Hello girls, today we are going to study about the deviation from Beers Lamberts law. So we have studied a Beers Lamberts law which states that A is equal to ABC, where A is absorbance, capital A is absorbance, small a is a constant at a given wavelength, and this is absorptivity. B is the path length and C is the concentration. Provided that we are keeping B constant, so generally it is 1 centimeter, there is a direct relationship in between A and C concentration. So if the concentration of analyte is increased, the value of absorbance will also increase. So this can be seen from this graph wherein we plot absorbance versus concentration. And this is a central ideal behavior. So if you have an analyte and if you go on increasing the concentration of analyte, there will be proportionate increase in the absorbance value. So this is an ideal scenario. Sometimes we may get a deviation from the Beers Lamberts law. So there are two types of deviation, a negative deviation and a positive deviation. So in the negative deviation, the observed absorbance is less than that of the ideal absorbance, and this can be seen at generally higher concentration values. While in case of positive deviation, the observed absorbance is higher than that of the ideal absorption. So we call this as a positive deviation. So the deviations are generally classified into three types. First is true, real, or fundamental deviation. So these are the causes of deviation. The second one is instrumental deviation, and third is chemical deviation. Now we will see these deviation one by one. So true deviation or real deviation or fundamental deviation states that the Beers-Lamberts law is applicable to only dilute solutions. So if you increase the concentration of analyte, the deviation will be seen. And this kind of deviation at higher concentration, we call this as a true deviation. So this is generally seen whenever the concentration of analyte is greater than 0.01 molar. So whenever the concentration is increased, the molecules are brought close to each other and there will be electrostatic interaction, and these are going to affect the absorption by the molecule. So there could be scattering of light due to particulates in the sample, or there could be the fluorescence or phosphorescence in the sample, or there is a change in the refractive index whenever we are using a higher analyte concentration. So generally, refractive index of the solution ideally should be less than 1. So this condition is generally observed when the concentration of analyte is there in the range of 10 raised to minus 6 moles to 10 raised to minus 3 moles. If we increase the concentration, the deviation from Beers-Lamberts law is been observed. So change in the refractive index will be there with the increase in the analyte concentration. There will be increase in the refractive index of the media, and it causes the non-linearity by altering the position, size, or solid angle of the image transmitted to the detector. So in this case, if we write the Beers-Lamberts law as A is equal to epsilon BC. So here this epsilon is generally used whenever we are expressing the concentration in moles per liter. So at higher refractive index, now absorbance is also decided by, it is also dependent upon the refractive index. So this constant epsilon here is been replaced by this new constant epsilon n or mu, divided by mu square plus 2 whole bracket square. So this states that there is a relationship in between the refractive index and the absorbance. Now here the absorbance is not only dependent upon the concentration of analyte, but it also depends upon the refractive index of the media. So generally, refractive index of the sample should be less than 1. And as I've said, this condition is been seen at a concentration of 10 raised to minus 6 to 10 raised to minus 3 molar. The speed of light is reduced at the higher concentration and hence altering the refractive index. So at higher concentration, we see different kinds of interaction like solute-solvent interaction, solute-solute interaction, or hydrogen bonding. So that is going to change the environment of the analyte and hence changing the absorptivity. So this is first real deviation or fundamental deviation or a true deviation, which states that Beers Lamberts law is only applicable to the dilute solutions. So if we have a non-linear relationship observed at higher concentration, simply we have to go on diluting the solution during the measurement. Second kind of deviation is chemical deviation. Now here, there could be number of reaction or chemical reaction taking place, and due to that, you can see the deviation from the Beers Lamberts law. So there could be association, dissociation, polymerization reactions, and due to this, the nature of the chromophore could change, and the lambda max itself even can be changed. So this you can see generally in case of the pH indicators. Say if you take an example of phenol red, and which is yellow. Now yellow acidic form, you can see the lambda max of the compound is different, and when you say it is in the basic form, the color of the phenol red is red in color, and you can see that the lambda max of the phenol red in a basic media is different than that of the acidic media. So whenever we are doing any kind of measurement in a unbuffered solutions, so there could be the presence of both of those forms, and if the solution is unbuffered, in that case there could be the deviation from the Beers Lamberts law. But if you take care of having properly buffered solutions wherein either the basic pH or acidic pH is maintained, and here you can see that only the dye can exist in either of the one form. Third deviation is instrumental deviation, and instrumental deviation can be seen due to stray light or polychromatic radiation, or due to scanning speed, or due to unmatched coverts. So if it is polychromatic light, so you can see that there are more than one wavelength present. So generally, Beers Lamberts law is, you can see that we are using a monochromator, so that the monochromatic light means the light having only one wavelength is being sent onto the sample cell. Now, if you see that there is a polychromatic light, you will certainly see the deviation from the Beers Lamberts law. So generally in the instrumentation, what we have is a source of radiation. This source of radiation is followed by the monochromator. So this monochromator is expected to convert the light into the monochromatic one. So if you are say sending a band of source is emitting in the range of 200 to 400 nanometer, and if your monochromator setting is been set at 250 nanometer, it should only send 250 nanometer onto the sample cell. But this condition is rarely seen. So each monochromator has its own band pass. So some of the monochromator has narrow band pass, and some of the monochromators have a broad band pass. So generally, you can, if you are working up with a non-monochromatic radiation, we can minimize this deviation by using a relatively flat part of the absorption spectrum, such as the maximum of the absorption band. So if we have two peaks in a compound, say one is relatively flatter and the second one is very sharp, so it is always preferred to work on a flatter curve rather than working on this kind of pointed curve. So here in this case, what kind of wavelength is been selected for the measurement, it decides the deviation, or it decides the measured absorbance value. So generally we operate at the flat portion of a band rather than working on the sloping portion of the band. If you have a non-monochromatic radiation, say if you work up here with band A, okay, so if you select something, some wavelength from this portion, this flatter portion, you will get linearity observed. So there would be a linear relationship in between the absorbance and concentration. But if you see that if you choose any kind of wavelength in from band B, so here from the sloping part, say this could be this part, or this could be, or this rising part, any one part, if you select any one here wavelength for measurement, in that case you're certainly going to have a deviation from the Beers Lamberts law. So you can see for the same drug, say my concentration is 10 microgram per ml, and if I choose here say 250 nanometer as the lambda max or the wavelength of measurement, in that case I am going to get this line. But if I choose something out here, say for example 225 nanometer, in that case we are going to have a deviation from the Beers Lamberts law. So although the concentration is 10 microgram, we are having different absorbances value. So here you can see okay, so you can see the deviation from the Beers Lamberts law. At one wavelength, you'll get a linearity, perfect linearity, and at the second wavelength, which is on the sloping part of the band, you are going to get a non-linear relationship. So generally in UV spectrophotometer, we have to use a wavelength selector, which will try to give us a monochromatic radiation. So that depends upon the bandwidth of the monochromator. So some monochromator has a larger bandwidth, say 200 nanometer. That means if you select 300 nanometer to be made incident onto the sample, it is just going to send something from 200 nanometer to 400 nanometer. Okay, so 400 minus 200, it would be 200 nanometer. So the bandwidth or band pass of the given nanometer is 200 nanometer. Or if you select something from a narrow band pass or narrow bandwidth, so here in this case, now if you select, this is the band pass of 50 nanometer. So now if you want to make 300 nanometer incident onto the sample, so your monochromator is going to pick up the wavelengths from 275 nanometer to 315 nanometer. So 315 minus 275, so it would be 50 nanometer. So here the monochromator is working more precisely in comparison to this case, wherein the band pass or your non-monochromaticity is been observed. More non-monochromaticity is been observed in this particular case. So generally, the monochromator performance is dependent upon the band pass. So narrow is the band pass, more is the monochromatic radiation achieved using a given wavelength selector. Now, what kind of slit width has been selected? That also decides the linearity in Beers Lamberts law. So if you have a source and from this source the light is passed to the monochromator, and then it is allowed to fall onto the detector. Okay, so you have started scanning, say monochromator source is going to emit something from 200 to 400 nanometer, and the monochromator will start sending first 400 nanometer, then progressively it will decrease and go up to 200 nanometer, and your detector is going to measure the intensity of each of the wavelength, and what you will see here, a plot of wavelength versus that of the energy of each wavelength. So whenever you are going to measure the light which is being emitted going through the monochromator and then directly falling onto the detector. So when you are interested or when you are measuring the light of the intensity of light directly coming from the monochromator, you say that it is this data will be helpful in measuring spectral bandwidth. Okay, so you are going to get first the band, and for this band, say what kind of band, you can see here something, a dotted line. So this is the energy at this particular wavelength. As you go on decreasing now the wavelength, the energy has reached the maxima, and then again it is going to get decreased. Okay, now when you take into consideration the height of this peak, so height of the peak, uh, this peak is been obtained by measuring the intensity of the light which is leaving the monochromator, okay, without a sample cell. Okay, now at the half of this peak height, so whatever width you are going to get, so that is going to be a spectral bandwidth. So you call this as a spectral bandwidth. The second parameter you can see is the natural bandwidth. So for natural bandwidth, we are going to operate, we are going to use the same phenomenon, and here the sample cell is been placed. So now in natural bandwidth, it is the width of the sample absorption band at half of the absorption maxima. So this is your sample absorption band, and at this maxima, you can see that here in this case, in this particular case, the spectral bandwidth and the natural bandwidth, both of them are same. Generally, for having a perfect linearity, it is preferred to have a spectral bandwidth which is 1/10 than that of the natural bandwidth. So your spectral bandwidth SBW has to be 1/10 to that of the natural bandwidth. Means what? If we record the natural bandwidth and it is coming out to be 200 nanometer, 1/10 of this 200 nanometer is 20 nanometer. So the spectral bandwidth should be ideally less than 20 nanometer, so that you will get linearity in your Beers Lamberts law. Next component is stray light. Now this is something unwanted radiation reaching to the detector other than the wavelengths normally transmitted by the monochromator. So generally this arises due to imperfection in a monochromator or in the optical surfaces. So here you have a source is followed by monochromator, and monochromator is desired, it's going to say send 200 nanometer. So apart from 200 nanometer, if it is sending something else also, so we will call this as a stray light. So this stray light generally is been originating from the imperfection in the monochromator itself or other optical parts. So there are number of windows present in the transmitting windows present in the spectrophotometer, if there is going to be imperfection in any one of those parts, so it is going to give rise to stray radiation. Now this stray radiation, you can see that it is a component of it is present in along with the incident radiation and the transmitted radiation too. Now whenever you are not keeping the sample in the path of light, and whenever you are going to measure the intensity of source, so you will call this as an I0. Okay, and whenever you keep the sample cell in between your detector and the source, the intensity of light is going to get reduced, and then due to absorption, and then what you measure is the transmitted radiation. Now if you have this monochromator and if it is giving rise to the stray radiation, so this stray radiation is going to be present along with the incident radiation too, and it is also going to be present in the transmitted radiation. Now how it is going to affect? Now suppose my intensity of incident radiation is 100 and the intensity of transmitted radiation is 50. So what ideally I should get is a log of 2. Okay. Now when you see that the stray radiation is there, so stray radiation, suppose now the value is 20, and here also the value is 20. Now you can see that this parameter is been significantly raised in comparison to this. So it will be 120 divided by 70. And this is certainly less than 2. The value is going to be less than 2. Means the absorbance value is going to get decreased. So if the stray radiation is going to be there, now this stray radiation is going to be the part of incident radiation also and the transmitted radiation also. But it is going to impact the intensity of incident radiation more in comparison to the transmitted radiation, and hence overall you can see that whenever the stray radiation is present, it is going to give decrease in the absorbance value. Okay, so sometimes you can even see the spurious maxima. So ideally this is the ideal case of absorption. This ideally should be the seen, but you can see that a spurious maxima is seen due to the stray radiation. So this stray radiation is more evident at higher absorbance values. Means the intensity of transmitted radiation is going to be less. So you can see as the amount of stray radiation goes on increasing, the value of the true absorbance is going on decreasing. During the measurement, if you're using a double beam UV visible spectrophotometer, we ideally should work up with the matched cells or cuvettes. So if so cuvettes are obtained with their percentage matching certificate. So these two cells should ideally have uniform surfaces and matching surfaces. Their transmission characteristics should be same, and if these conditions are not followed, means if the two cells are differing in their path length or their optical characteristic, then also we are going to get a deviation from the Beers Lamberts law. Lastly, even you can see the deviation from the Beers Lamberts law due to the scanning speed. Okay, so whatever detector is going to record the intensity of the light, so that signal is being fed to the pen recorder, and that pen recorder is going to continuously monitor or it's going to continuously record the intensity or the absorbance values. Okay, now this is an ideal scenario at around average speed. Now if the speed of the pen recorder is been increased, so that it is going to lost its fidelity, and there could be the electronic or mechanical dumping of different parts of the recorder, and it cannot cope up with the higher scanning speed. So generally in this case, the direction of the record or your spectrum is been shifted in the direction of scanning speed. Means you can see here that this was an ideal scenario. If you go on increasing the scanning speed, suppose this record is of 1 nanometer per second. Okay, and if now you increase the scanning speed, what is going to happen is your spectra is going to shift in the direction of scan. So this is the direction of scan. The spectra has been shifted in the direction of scan. Now the scanning speed is so high that the recorder cannot cope up, and rather than going or giving the correct absorption at the lambda max, it is just going to take the shortcut. Okay, and at the lambda minima, again, rather than going down and making the record of the lower absorbance value, again, as it cannot cope up with the speed, it is just going to give us the higher absorbance value at the minima. So this is the maxima and this is the minima. So what had happened, the lambda max of the compound is being shifted towards the left, means there is decrease in the lambda max. Okay, the second thing is the absorbance value is going to get decreased at absorbance value at lambda max is going to get decreased, and the absorbance value at lambda minima is going to get increased. The spectra is being shifted towards the direction of the scan, and there would be the loss of resolution. Okay, so this is what, again, you can see something of this sort is going to be happening. Same way, if you still increase the direction, if you still increase the scanning speed, there is shift. You can see that lambda max is also shifted. Okay, decrease in the absorbance value at lambda max, increase in the absorbance value at lambda minima. Okay, so this way even the scanning speed is going to have effect on a Beers Lamberts law. So this way we have seen three kinds of deviations from the Beers Lamberts law. First is